Today in Lecture 11, we're going to explore the new science of electricity. The 18th century was a real century of achievement where electricity was concerned. Electricity was one of those phenomena of our experience that seems to involve a material substance and not involve a material substance at the same time. We've been running into this kind of thing for several lectures now. Mesmer, as we saw last time, appealed to the flow of an imponderable fluid to explain disease. His fluid was one of these elusive entities that both is a material substance and is not a material substance. And we heard Mesmer say in that lecture that animal magnetism was like the matter of light. And then there were the chemists. Chemists also appealed to an imponderable substance, phlogiston, and they drew on it for a great part of the 18th century, some right on into the 19th. Don't forget the chemist Lavoisier's explanation of combustion. He explained it as the adding of oxygen, ordinary matter. But remember, Lavoisier believed, and he was hardly alone in this, that the matter of heat, which was weightless, was joined to the air, and that it separated from air and was released when something burned. There's another imponderable substance, heat. So far we have phlogiston, heat, light, magnetism, Mesmer's animal magnetism, all imponderable substances. Let me point out again that these imponderable substances were extremely fruitful ideas for natural science. I know these imponderable substances raise the interesting question of the status of hypothetical entities. And we'll get to that issue when we deal with something called the ether in the 19th century. It's the next to the last lecture of the course. But the fact that they raise this kind of question is just the point. Imponderable substances have been very helpful to the development of natural science, and we need to appreciate them. In this lecture, we'll meet the imponderable fluid whose flow explained electricity. It will be different from Mesmer's animal magnetism, more like heat, light, and phlogiston, because the existence of electrical fluid, or as Franklin liked to call it, electrical fire, was accepted without much question as the basis of electrical phenomena. One of our goals today, then, is to see how this came about. As we've done before in other lectures, we'll first explore the ideas that the 18th century inherited about electricity. Then we'll follow the success of new ideas of some very creative minds. In particular, we want to learn something about Benjamin Franklin's work. Franklin was quite famous all over Europe, and his fame emanated largely from his work in taming electricity. Before we're done in this lecture, I think you'll understand why Benjamin Franklin is a worthy figure for us to get to know. Well, let's take a look at the heritage of knowledge about electricity that came into the 18th century from earlier periods. From ancient times, there was an interest in the property of amber. If you rubbed amber, it displayed a certain power to attract objects. Of course, as time passed, natural philosophers studied this phenomenon. They also noted the attractive power of magnets, but magnetic attraction worked only in iron. Amber's curious capacity to attract objects after being rubbed existed in other materials as well. And natural philosophers called these substances that behaved like amber did electrics, because they exhibited the electric effect. How did they explain it? Well, some believed it to be an occult power. Something hidden was doing the attracting. But most natural philosophers weren't inclined in that direction. They insisted on explaining it as an interaction among different kinds of matter. This, of course, was in keeping with what we've been observing about natural philosophers. Certainly, as we come into the 17th century, the preference was to assume that something natural was happening and needed to be explained, possibly even captured in a natural law of some sort. It was really in the 17th century that systematic experimentation on electrical and magnetic attraction was undertaken. I suppose it would have been surprising if this hadn't been the case. It was a century of incredible activity in the exploration of nature, so along with what Galileo and Kepler were doing in studying the heavens, and Harvey was doing in studying the human anatomy, and what Boyle and Becker were doing in chemistry, and I haven't even mentioned Newton yet, with all of this upsurge of activity in the study of nature, it just stands to reason that there would be an interest in studying electrical and magnetic effects as well. And there was. A considerable amount of experimentation went on in the 17th century. It was a time to gather information. Now, I want to make a special effort here to give you a sense of what these experimenters were up against. Electrical effects, in particular, can be bewildering. You might not get the same results from one day to the next because there's so many variables that affect the outcome. And you don't even know what the variables are. Think about it. Suppose you learned that rubbing a certain kind of material not only attracted small objects like feathers to its surface, but could even give you a little shock if you brought your finger close to it. And then the next day you try it and you get nothing. Would it occur to you that the humidity might be the reason why it worked on one day and not in the next? We have to remember that these experimenters were on the front side of electrical knowledge. They're starting from ground zero. Things began to pick up in the early 18th century. This was because a number of new electrical instruments were invented that helped natural philosophers to produce impressive electrical effects more efficiently. And an important figure here was a man named Francis Hauksbee. Hauksbee became the chief experimenter at the Royal Society when Isaac Newton became president in December of 1703. He developed a means of producing electrical attraction using rubbed glass that quickly became standard. What he did was to figure out a way to make the rubbing of glass much more efficient than it had been. He mounted a glass globe on a spindle. Then he connected the spindle to a crank so that when he turned the crank, and the globe spun rapidly. Now all you had to do was to hold your hands or a wool cloth under the spinning globe, and you could produce the effect much more efficiently. The major impact of Hauksbee's new method of producing electrical attraction was that the attraction was much stronger than anything you could get by just rubbing glass or by stroking it. And that made a big difference. As you can imagine, it opened up a whole set of possibilities for others to create experiments. Natural philosophers were discovering that this force of electricity was becoming significant. Who knew how powerful it might become? Another innovative discovery came with the work of Stephen Gray in England. In the 1720s, he realized that the electrical effect could be communicated. He'd been working with a glass tube, and when he rubbed the tube, he could show that a feather would be attracted to the tube. Now, there's nothing novel in that. Well, at the time, others had noticed it. But then he put a cork stopper in the end of the tube, and he noticed that the feather was attracted to the cork. Apparently, the attractive capacity had been communicated from the glass to the cork. So he tried to see if it could be communicated farther. He stuck a stick into the cork stopper and then attached an ivory ball to the other end of the stick. And then he rubbed the glass again. And he was able to show that the feather was attracted to the ivory ball all the way out at the end of the stick. Now, he and everybody else wanted to know how far the effect could be communicated. So these early electricians started testing. In the process, they discovered what materials were good at communicating the effect and which ones weren't. They also discovered something else. For a while, it appeared that the effect could not be communicated over long distance at all in the horizontal direction. Vertical was okay, but not horizontal. If your communicating line went straight up into the air, even quite high, and you rubbed the glass below, the effect could be communicated to an ivory ball all the way up at the top. But if you laid the apparatus down horizontally, it wouldn't work. Of course, this seemed very odd. But then maybe that's the way nature was. We're learning here. If some of these electrical effects depended on whether the day is rainy or not, then why would you be shocked and surprised if they worked in a vertical direction but not a horizontal one? Well, it wasn't long before they realized that the problem wasn't because of the horizontal direction. They discovered that the communicating lines had to be kept from touching the ground. If the line running from the glass tube touched the ground, attractive force couldn't be passed along a line to a distant point. So they took to suspending the lines in air using silk cords. That seemed to work just fine. Now, just after this, in the early 1730s, the head or intendant of the Garden of the King in France Buffon would hold that position 2 decades later, and I mentioned him earlier. The intendant heard of Gray's experiments and started doing some of his own. This was the natural philosopher Charles Dufay. All this experimenting made clear that you could distinguish between 2 different categories of substances. One kind was like glass and amber. You could rub it and produce the electrical effect. As I mentioned earlier, people had known about this amber effect for a long time, and they knew that there were more substances than amber that could be used. But they used the Greek word for amber as the basis of the name they gave these substances. Amber in Greek is electron. We see here the vocabulary of electricity beginning to form. These substances, which when rubbed showed the attractive effect, had come, as I mentioned, to be called electrics by the time you get to the 18th century. The other category of substance was the kind that you could use for leads, to lead or conduct the effect from where you were rubbing to the glass to a distant point. These were called non-electrics because they were not like glass. You could rub them all day and they wouldn't show the effect. Non-electrics were substances like wood, thread, or even the human body. They were used to communicate the effect from one place to another. But Dufay also found that things were just a bit more complicated. He realized that there were certain circumstances under which electrified substances repelled rather than attracted. What was going on here? Dufay concluded that there were 2 different kinds of electricity responsible for the 2 different kinds of force produced. He had an enthusiastic assistant, a young priest named Jean-Antoine Nollet, who became very involved in the study of electricity. Nollet was a Cartesian. His world was filled with matter, no empty places anywhere for Descartes in his world, and the matter had to act and interact mechanically. Nollet envisioned electricity as an imponderable fluid. It was present in all bodies, and this fluid could be set into motion by rubbing, if you have an electric, or by contact if you're dealing with a non-electric. Once you get it into motion, the fluid flows out from the excited object. But remember, for a Cartesian, a vacuum is impossible. So something has to take the place of the fluid that flows out. By the mid-1740s, Nollet had come up with an elaborate theory of effluent and affluent flows, outgoing and incoming fluids. In this way, he was able to account for a great deal of the experimental results that he, Dufay, and others in Europe had been gathering. By this time, they had learned how to do more than merely attract and repel various objects using electrical forces. They also knew how to produce shocks that could be felt as the electrical fluid passed through the body. And they knew how to produce sparks that you could see. This was a fascinating field of study indeed. Now, as you can imagine, news of these developments spread all over Europe in the 1730s and the 1740s. The German states were no exception. And it was here that another intriguing aspect of the story began, in Leipzig, at the university there. A natural philosopher named Georg Bose set up experiments using what by then was the standard technique of producing electrical sparks by rubbing a spinning glass globe. Bose got the idea of enhancing the effect by communicating it in dramatic ways. For one, he suspended an iron bar from the ceiling using silk cords, and then communicated the electrical effect from the spinning glass globe to the bar. In another, he used the same arrangement, but ran leads from the barrel into a glass of drinking water and drew sparks from there. Now, Bose was not above getting all the attention he could from this kind of demonstration. He performed feats like this for spectators, including noblemen, and for the king. In one famous case, he claimed to have had a woman stand on a platform, in an insulated platform, while she was being electrified. And then when he proceeded to give her a kiss, well, it was a mildly shocking experience, to say the least, and very impressive. Bose's demonstrations caused a lot of interest. When word reached Prussia, a clergyman there named Ewald von Kleist became intrigued. As a younger man, he had studied natural philosophy in Holland, and he'd never lost his natural curiosity. So he decided to replicate Bose's experiments when he heard about them. In the course of doing this, he tried his own means of enhancing the effect. He set up Bose's arrangement of suspending an iron bar, might have been a gun barrel, from the ceiling, and ran leads from the spinning glass globe up to the barrel. The bar, or the gun barrel, incidentally, was becoming known as the prime conductor. Now, he thought he might be able to get a greater shock if he increased the mass of the prime conductor even more. But how? Well, he ran some more leads from the gun barrel to a glass flask that he held in his hand, which was partially filled up with water. So now he had the mass of the barrel and the flask of the water. The leads from the barrel ran down a nail that penetrated through a cork at the top of the flask that he held in his hand, while the electrical effect was being communicated to the gun barrel, presumably by an assistant. What he found was that while electrifying the flask, a flare appeared in the flask. He also noticed that he could carry the flask around the room, and the flare would linger a while. And if he touched the nail at the top of the flask, he could draw off a spark. He'd created a portable sparking machine. Now, there were some things about what he'd done that mystified him. One was this: to draw the spark from the jar, he had to hold the flask in his hand. That really surprised him. It wouldn't work at all if, for example, you put it on a table and then touched the nail. Or it didn't work as well. You had to hold it in your hand when you touched the nail. So naturally, he wrote about this to friends and acquaintances, and in his descriptions, he left out some important details, or at least he didn't make clear exactly how you had to do the experiment. And nobody was able to repeat the experiment successfully. Eventually, one of his acquaintances had success, or should I say his assistant did. Let me explain what the problem was. Everyone assumed that the prime conductor, the suspended gun barrel, in Bose's arrangement, had to be insulated if someone was going to draw sparks from it. Bose used these silk cords so that the gun barrel just hung there in midair. Dufay, in fact, had set that down as a rule. You had to insulate the prime conductor. Well, in von Kleist's arrangement, you have, in addition to the gun barrel, the flask. So whoever held the flask that was attached to the gun barrel would have to have been insulated too, according to Dufay's rule. Now, von Kleist hadn't done this, and he didn't make that clear. He'd held the flask himself as it was receiving the electricity. When his acquaintances tried to duplicate this experiment, they naturally followed Dufay's rule. They had one person hold the flask while standing on something that insulated him from the ground. Then that person removed the flask from contact with the gun barrel to see if it indeed had become a portable sparking machine. He presented the flask to another person who tried to draw the spark from the nail at the top of the flask, but it would never work. We'll see a little later why these two things von Kleist did unwittingly made it work. One, not insulating himself from the ground, and two, drawing the spark from the nail himself while holding the flask. Well, how did they figure out what was wrong? How did they finally realize that they should ignore Dufay's rule and that the one who touched the nail should be the one who held the flask? By accident. After trying over and over without success to draw the spark from the flask held by his assistant, von Kleist's acquaintance no doubt tried other arrangements, including one that ignored Dufay's rule. And then, when the assistant touched the nail himself, wham, they now knew. This happened in the spring of 1746. Same thing happened or occurred in Holland around the same time, just around the same time. A professor of mathematics and philosophy at Leiden was trying an arrangement similar to Bose's when he electrified the glass of water. He was following Dufay's rule of insulating all prime conductors, in this case, including the flask of water he was using. This time, the accidental discovery came about because of a lawyer who had visited the laboratory and knew about the experiment. He then tried to do what we're all told never to do. He tried to do it at home. But he didn't know anything about Dufay's rule, that you should insulate the prime conductor, and he was all alone. There was no one else to hold the flask anyway. So he reached up himself to touch the nail after he'd electrified the flask, and wham again. Naturally, he reported his experience to the professor, and they reproduced it quickly with great success. The professor, describing the experience of being shocked by the jar, said it felt like he'd been struck by lightning. And it was done in Leiden. This is where I want to bring in Ben Franklin. He'd been introduced to the subject in Boston in 1743 by an itinerant lecturer from Edinburgh. Franklin got him to come to Philadelphia the following year. Apparently, he put on quite a show, drawing sparks from a little boy who was suspended in the air. Then, in the fall of 1745, word of the German electrical experiments reached Philadelphia. It came by way of a Quaker merchant in London who had business connections in the colonies, but he was also a fellow of the Royal Society, and he had helped Franklin earlier. Franklin had been interested in collecting journals and experimental apparatus and other natural curiosities, and the merchant kept him in touch with what Europe had to offer. Well, that fall, in 1745, he'd sent a glass tube along with a copy of a magazine with an article describing what it called wonderful German electrical experiments, referring, among others, to Bose's impressive demonstrations. So by the winter of 1746, 1747, Franklin was really into it. By then, he'd heard about the new Dutch portable sparking machine, too, what became known as the Leyden jar. It was Franklin's great achievement to provide an impressive account of the machine, to give an explanation that made sense of what was happening and why. Here's what Franklin said. First, he asserted that electricity was a weightless substance that adhered to the surfaces of normal material bodies and whose presence there charged the object. In seeing electricity as an imponderable fluid, he agreed with Nollet. But unlike Nollet, Franklin did not believe that there were two different fluids, two different kinds of electricity. He felt that there was only one fluid, or electrical fire, as he liked to put it. And this electrical fire had two essential properties on which everything depended. First, it was attracted to normal matter. In fact, the amount of electrical fire that existed on the surface of a substance was directly proportional, according to Franklin, to the mass of that substance. So, for instance, let's say you have two substances, same size, same shape. First is made of some dense matter, say glass, and the second one is made of balsa wood. Well, clearly there's more mass in the glass than in the balsa wood. So more electrical fire will be attracted to the surface of the glass than to the surface of the balsa wood. Okay, that's property one. The second essential property of electrical fire was that it repelled itself. That meant if you can imagine it being released into some space, it would immediately spread out to fill that space. Now, given these two properties, what would be the case? Well, under normal conditions, the electrical fire would be both attracted to the surface of substances at the same time it repelled itself. So what's going to result is that there's going to be an equilibrium develop between these two tendencies. And that would mean, for example, in the case of a glass flask, like the one used in the Leyden jar, that an equilibrium would emerge between the attraction of the electrical fire to the surfaces of the jar and the electrical fire's repulsion of itself. The jar then would have on its surfaces, both inside and outside, a characteristic equilibrium amount of electrical fire after these balanced out. Now, Franklin used his idea of electrical fire to explain properties of electrics like glass or conductors like wire. Electrics like the glass globe surrendered their electrical fire from their surface more easily than others when rubbed. And conductors permitted electrical fluid to flow through them. Incidentally, since the Earth is such a huge mass, it attracts to itself an unimaginably large amount of electrical fire. Where electrical fire is concerned, the Earth is like a good well. You can always get as much electrical fluid or fire as you need from the Earth, and by the same token, the Earth can always receive as much electrical fire as you can give to it. One more thing, and you'll know everything you need to understand Franklin's explanation of the Leyden jar. It's this. Electrical fire itself cannot penetrate through glass. It stays on the surface. But, and here's something very important, the repulsive force it exerts. Remember, electrical fire repels itself. This repulsive force can be exerted through glass. This means that if I have electrical fire inside a flask, it can't get out. But the repulsive force it exerts does extend right through the glass. Okay, now we're ready to hear what Franklin said was going on in the Leyden jar experiments when natural philosophers created portable sparking machines. What happened, according to Franklin, was a disruption of equilibrium. In the standard arrangement, a revolving glass globe is rubbed, and the electrical fire on the surface of the revolving globe is led away up to the prime conductor like a gun barrel. You can think of it as a flow of red that goes up from the globe to the gun barrel. From there it goes along the barrel and then down through a lead to the nail in the top of the flask. You could now walk away with the electrical fire and it would stay inside the flask. It can't get through the sides of the flask because it can't penetrate glass. So it piles up inside the flask on the inside surfaces of the jar, on the surface of any water that might be in the jar. But this means that the equilibrium amount of electrical fire that was on these surfaces has been increased. We don't have an equilibrium any longer. Now, what do you think happens when you get an excess amount of electrical fire trapped inside the flask? It can't get out, but there's an excess amount of repulsive force that can get through the glass. And here's what Franklin says that does. The excess repulsive force acts on the normal amount of electrical fire that was already on the outside surface of the jar. What does it do to the electrical fire on the outside surface of the jar? It repels it. It drives it away through the body of the person holding the flask and into the ground. And what are we left with? A very unstable situation. We've destroyed the normal equilibrium that existed inside the jar by piling up an excess amount inside the jar and created an abnormal deficiency on the outside of the jar. Now we can carry this jar to another part of the room and the unstable situation will stay the same. The excess electrical fluid remains stored inside. And now we understand why the same person who holds the flask has to be the one to touch the nail. Because it's that person's body that will let the equilibrium be restored. Why? Because only if there's a route from the inside surface of the jar, where the excess fluid is, to the outside surface of the jar, where the deficiency is, can the equilibrium be restored. So the same person whose hand is in contact with the outside of the jar has to touch the nail which connects him to the inside of the jar. And when he does, wham! He feels it as the excess electrical fire inside travels through his finger, down his arm, across his chest, and out the other arm to the outside of the flask. Beautiful explanation. For Franklin, the explanation of lightning was similar. In the sea, salt particles, an electric, rub up against those of the water conductor, causing an excess of electrical fire to gather on the surface of the sea. When the water evaporates, the excess weightless electrical fire is carried to the clouds. Now the cloud floats past a projecting object, say a church steeple. If there's enough excess electrical fire in the cloud, it will jump to the earth, which can take as much as necessary to restore the normal equilibrium. As many of you know, Franklin became famous for proving his theory about lightning, being electricity, and for taming electricity, for suggesting that lightning rods provide a safe means for letting the excess electrical fire get into the ground without going through the steeple on the way. He was a remarkable figure. There's a great deal more that could be said. Nollet criticized Franklin. The big disagreement between them was not only that Nollet thought there were two fluids, not one, but also that Franklin was saying that the electrical force could act at a distance when it repelled itself. For Nollet, the Cartesian, that was anathema. He couldn't do that. But the next major development, which doesn't come until much later in the century, involved electrical discharge and living things. And we're going to turn to that in our next lecture.